All right, hi, welcome back. So section 4.5, we're gonna go over that. In this section, we're gonna introduce the derivative of the logarithmic function, and we're gonna use this to solve real life logarithmic problems. So in the last section, we reviewed the importance of the logarithmic functions in real life applications. In this section, we'll extend these applications by analyzing the rate of change for this function. Just as we found the derivatives of other functions, we can also find the derivative of this log function by using the derivative limit definition. Now, instead of actually doing that, for the purpose of time and focus of this class, we're actually going to give you the actual rule. But you can easily do this using the limit definition. So, okay, let's begin. So for this table, let's assume that u is a function that is differentiable um, um, in terms of x. So let's take the derivative. Let's say if I ask you to find the derivative of a log function base b, right? Log of x base b. So the derivative of this will be 1 all over your x, right, times 1 all over the natural log of your base, right? And that would be it, right? But that's the case where you just have x. Let's say the case where you actually have a function. So if you think about it, just any function, right? Like g of x, a function is in terms of x. So we can agree that this is the inside of the function and the log is the outside of the function. So we see here that we have a function inside a function, so therefore to take the derivative of this we have to use the chain rule. So the chain rule says you take the derivative of your outside first. Well, the derivative of the outside, by definition, as we've seen before, is 1 all over whatever the inside of the log is, right? So we're going to copy and paste whatever that is in there, right? Simple enough. And then times 1 all over again the natural log of your base, right? That's as we did it before, right? As we did it over here. But because we have a function inside a function, we technically have to multiply at the end by the derivative of the inside, right? The derivative of the inside. So that's because, again, by the chain rule. So the chain rule applies here, and is always applied whenever you have a composite function that is a function inside a function. More important, we actually focus a lot in using the natural exponential function that is ln of x. So if I ask you to find the derivative of ln of x, we actually have a more tailored rule for this, but nonetheless it does come from here, and I'll show you guys that in a second. But so if I ask you to find the derivative in respect to x of the natural log of x, then what we gotta do is 1 all over your x, right? And if I ask you if we actually have a function inside this natural log, again, this is the inside, the log is the outside function, right? So we have to apply chain rule. So the derivative of the outside is 1 all over, right, the inside. The inside stays the same, right? Keep the inside the same. And then you multiply by the derivative of the inside by the chain rule property. Now you might ask, like, well, why are these not included there? It's actually a very simple question. It's there. It's just we never actually have to use it. For example, if you think about the natural log of x, this is equivalent to the logarithm base e of x, right? And if I ask you to find the derivative of this, right, then we know that we have to follow this rule, right? 1 over your x times 1 over the natural log of your base. Well, in this base, the base is e, right? Because that's your natural log. And what do we know about what happens when you have the natural log of e? This turns into a 1. So basically you have a 1 over a 1. So why write that, right? Why write 1 over 1? So that's the same as 1, right? So why write this? So that just turns out to be 1 over x. So technically it's there, we just don't bother writing it anymore. And it easily applies again with the natural log of u as well. So moving on to the next special property, This is sometimes useful, but now with calculators it's not as useful because we can, just put in the calculator. Um, but this is a special property that allows us to change the base of a logarithm. So this is just easy for us to compute. So before, we it was a very practical for us to change the base of a logarithm. So if you notice, this is equivalent to a quotient of logarithms. If you notice here, what you can do here is you take the log of x all over the log, that's a typo, log of b, right? Of your base there. And what you can do here is you change the base to wherever you want. Now those have to be the same, right? So one example of that will be when you have base 10, right? Base 10. Well, because that's base 10, that's a common logarithm, we have a special notation for that one. That means we don't include the number there, right? But the number is 10 there, right? Even though we don't write it, it's a 10 there. The other one is whenever you have a base e. But we know that base e is the same thing as the natural log, right? So let me fix that. This is supposed to be log. So that would be whenever you have a base e here, that is exactly the natural log. Now the reason why we like to change it to natural log or base 10 is because we can use those in the calculator. All right, so moving on to a few examples here that we have. We're gonna find the derivative of the following expressions here. So in the first one, we just simply have a logarithm base 8 of x, right? So they're asking us to find the derivative of this. So as we said before, the derivative of the logarithm of this is going to be 1 all over whatever the inside is, right? That is 1 over x. And then, of course, you have to multiply by 1 over the natural log of your base, right? And that's it, right? That's pretty much it. But we can also say, oh, we can multiply these two together, numerator with numerator, that gives us the 1, and then denominator with denominator, and we get x times the natural log of 8. And that's pretty much it, right? That's just from here to here is just algebra, but of course we ended up using the derivative rule for the logarithm functions. All right, let's try another example here. In example B, we're looking for the derivative of 6 times the logarithm base 4 of x plus 17. So it's almost the same as before, except here that we have to consider the fact that we have a constant multiple, right? A constant being multiplied to a function. So remember, what is the constant multiple? It tells us that, oh, we just carry the constant and then we multiply by the derivative of the logarithm, right, of this function. What's the derivative of this logarithm? 1 over what's inside times 1 all over the natural log of your base, right, which is 4. And then plus the derivative of 17. But the derivative of 17, because it's a constant, is 0, right? So we would have added a 0 there, so we didn't, because it's just 0. And like before, we will multiply the numerator with the numerator gives us 6. Denominator with denominator gives us x times natural log of 4. And that's pretty much it. In the next example, we're gonna find the derivative of the function as well. In this case, we're given a little more things, but we also want to make sure that we remember to set up the function. If we notice, this one is in the form of a square root, and it is practical for us to convert this in terms of exponent, right? X to the 1/4. So that's what we did in the next line. This stays the same, except this one turns into x to the 1/4. Now that is ready. We haven't taken the derivative. That was just rewriting the function. Now we can take the derivative. So the derivative of this one is going to be, well, it's a constant multiple of a function. The constant is carried over, multiplied by the derivative of the function. The derivative of the function, being a logarithm, base 5, is going to be 1 all over the x times 1 all over the natural log of the base, which is 5, right? And that's it, right? And then followed by the derivative of negative 4x to the negative 8. For this one, we just have to use power rule. So we bring down the negative 8, multiply by negative 4, and then take away 1 from here. So that's that part. That's power rule. For this one, we're gonna take bring down the power and then subtract 1, right? Power rule, bring down the power and subtract 1 to the x. And that's it, right? We use the constant multiple rule along with the derivative of the log function. And then for these two, we ended up using the power rule. And then that was it, right? We already took the derivative. All we gotta do now is basically simplify by doing some simple algebra, multiplying 4 with 1 and 1, and then by 1, right? So 4 times 1 times 1 is 4. X times the natural log of 5 is x times the natural log of 5. Negative 4 times negative 8 is positive 32. X to the negative 8 minus 1, those add up to negative 9. Plus, and then 1/4 times x to the 1/4 minus 1, which is negative 3/4 by using the algebra.